to review this stuff, we have to remember how to do probability. So the first example is, what is the probability of drawing a queen or a king from a standard deck of 52 cards? So probability was always equal to what you want the number of outcomes you want versus how many are possible. Best way to think of probability is like a test. There's 20 questions on a test. What I want is 20 out of 20. I think that would be probability. What you actually end up with is what you actually get divided by what was possible. Hopefully it's 20 out of 20. So in this question, it's pretty simple. They said, what is the probability of drawing a queen or a king? Well, there's 4 queens, there's 4 kings. So how many things total are there that I want? There's 8 things that I want. Divided by how many possible things could happen? 52. There's 52 cards in the deck. So there's 52 possible things that could have happened. 8 divided by 52, that right there would be your probability of drawing a queen or king. Just for layman's sake, we want that lowest terms as a fraction. So I think it would be 2 out of 13. You can put in your calculator. What was it,
Percent is 15%.
Okay, so that's 3 different ways to write the same answer. But the review here is probability is what you want divided by what you could get. Question 2. What is the probability of drawing a card that is a heart, replacing the card, and then drawing an ace? That's a lot more complex, isn't it? So if you want to do this, you have 2 situations here. So what did we do with 2 situations? In the probability unit, we multiplied them because we wanted both things to happen. It was this and this. If it was this or this, that's when you're adding. When it's this and this, we're multiplying 2 probabilities. You're going to do your first probability, which was the probability of drawing a heart. There's 13 hearts in the deck, divided by 52 total cards in the deck. You want to times that by then drawing an ace. There's 4 aces in the deck, divided by 52 possible aces. You put that in your calculator, your math bracket. So what do you end up with? I think it's going to be like 1 over 52. Is that what it is? Put in your calculator, math bracket, 1 over 52. So that's your review on probability. What you want divided by what you could get. You multiply things together if both things have to happen. Reminder, what is our probability formula? Probability equals number of outcomes you want divided by total number of outcomes. Where this comes in handy for us, and how perms and columns come together. Remember with perms and columns, we've talked a lot about, like, here's 10 kids, what's the probability, not the probability, how many ways could I have a committee with 2 girls and 2 boys? But we also have questions like, here's 10 kids, how many possible committees are there? What you've been doing the whole time is calculating what you want, and you've been calculating what's possible. But we just haven't been linking them together yet. But you've already been doing it. How many different numbers can you get if you have a 6-digit number? Well, you would always figure out your total possibility, and then the next part of the question was always, Now, what if the second digit has to be a 7? Right? You've already been doing this kind of stuff. You just haven't been bringing them together into probability questions. So if we look, we said, the up order there. The example, when drawing a 5-carded hand from a standard deck, how many hands could you draw? No restrictions on this thing. So you have a 5-card hand, how many ways can you do it? You first have to ask yourself, is this a perm or a com? You know, if it's a perm or a com, just say, does order matter? Does the order matter how you're getting these cards? Does it matter if I get an ace and a jack, or the jack and then an ace? No, so order doesn't matter. Permutation order does matter, combination order does not matter. So this is a combination. And you always need to be asking yourself that. Which type of question do I got? This is a combination, because order does not matter. Now they want to know how many ways could you draw 5 cards from standard deck. Well, we know it's a combination. So we know that there's a C. The first number is the total number you're taking something from. So how many total are there? So it's 52. C, however many things you actually want. We want 5. So if you go 52, C, 5, you should get, what did you get, take?
2,059,598,960. Sorry, I didn't say that.
That's okay, that's fine. Yeah. 2,598,600?
Yeah. Or 2,598,9.
Oh, sorry, 9?
960. Yeah.
That's the total number of hands you could get. That's everything. It's everything from you got all aces and a king to you got 5 random cards that don't match up at all. Now question B says, what is the probability of drawing? Well, if you want to figure out the probability, you need to then do what you want divided by what's possible. What we just calculated, that is the total possible number. Hello. No restrictions means that's what's possible. Now, we're going to figure out what's the probability of all hearts. So that means you need to do what you want divided by what's possible. So how many ways could we get what we want? And this is something that we did a little bit, but these were hard questions. So if you want all hearts, how many possible hearts are there in the deck? There's 13 of them. Does the order matter which I'm taking them out? No, so it's C. And how many of them do you want? 5. So there's 13 hearts. You want 5 of them. How many ways can I pull 5 out of 13, T?
1,287. Sorry.
So 1,287, that's the total number of things I want. If you want to do probability, you're doing what you want. 1,287 divided by what's possible. 2,598,960. Now, for numbers like that, they usually just change them into a decimal, and that'll be your final answer. So if you change that into a decimal, you should get 0. How many zeros?
I got 4.9. So it's got
Could you times by 100? Times what? Oh, times 10 to the power negative 4. Thank you. So that'd be 0.0000 and then 4, and then 9 something?
Yeah.
4, 9? Okay. Remember that times 10 to the power of negative 4, the e to negative 4, is telling you that you need to move the decimal 4 spots left.
Would you rather have it that way or times 10 to the power of 4?
Like that works.
Okay.
Yeah. Do you have to write it like that? Can you write it? I'm just thinking multiple choice test, that's how it's showing up.
Okay.
If it's a written response, I'd be happy with whatever you gave me as long as I can make sense of it.
Okay.
Alright, number 2. What's the probability of drawing exactly 2 hearts? This is even a little harder. So, if I want probability, I want total number of what I want divided by total number. Total number of what I want is 2 hearts. So to calculate that, I ask myself, how many hearts are the deck? There's 13. Does the order matter in which I yank them out? So it's a C. The order does not matter. How many hearts do I want? 2. So I want 13 hearts. I want 2 of them. And I need 3 other cards, but they can't be hearts. So how many cards are there that aren't hearts? 39. I went 52 minus 13. So I took the 52 possible, got rid of the 13 hearts. I don't care the order. I want 3 of them. So that's 2 hearts and 3 non-hearts. If you put that in your calculator, Tay, what'd you get? Oh, you did right now.
71,000. Oh no, I am reading it wrong. 71, or I times them already. Is that what you want?
Yeah.
Okay, 712,842.
842?
Yeah.
So that's the total number of outcomes we do want. Now what's the probability of getting that? Now you divide by the total number of outcomes. So the probability of that actually happening is 712,842 divided by 2,598,960. That's the probability of that actually happening. You put in your calculator, it's going to be somewhere around 0.3 something. 0.27. Which means there's a 27% chance that that happens. You get exactly 2 points. Yeah, did you say wait? Do you have a question? Oh, okay. I was like, yeah, I'll answer your question. What do you want? Is this making sense? See how you were linking the 2 things together? It's really not that crazy complex because we've actually been doing the 2 parts the whole time. We just haven't been linking them yet. And now we're linking them to figure out probability. So for part 3, 2 queens. And part 4, a 2 and a 3. I want you to try them on your own and see what you get. I'll show my work up here. Talking our way through the 2 queens question. The first part, I had 4 queens. I chose 2 of them. And, so multiplication, I had 48 queens, or non-queens, I chose 3 of them. If you had done Hannah's situation, which what she asked was like, what about if you have 3 queens or 4 queens? Then you would have to do this situation, or, so plus, 3 queens, and then 2 random cards. Or, so plus, 4 queens and 1 random card. And you have to figure out all 3 things and add them together. So that is like a feasible question that you could get asked one day. And it's not like out of the realm of what we're doing. Or just keep it simple for now. I don't have much work room to do that type of question. When I do that, I got 103,000. I do my division. I got 0.04 as the probability. The last one was drawing a 2 and a 3. So I actually have 3 parts to this one. I chose my 2. So 4 2s, choose one of them. I chose my 3, there's 4 3s, I chose one of them. And then I chose my 3 other cards from the 44 things that weren't 2s or 3s. When I multiply all that together, I got 211,950. 4. I then did my little fraction, and I got 0.08. How many people got those things? Pretty good. Alright, last 3 examples. I'll do the first one, and then let's do the other 2. And I do want it to be clear that you could still do some of these questions that are probability questions with the fundamental counting principle, like the old school way that we did it. It was like this and this and this. Like that's still possible. Okay, it's just much quicker to use perms and coms. So this thing says, Mr. Kennedy is selecting a 4-digit PIN for his debit card. What is the probability he selects a PIN that doesn't have any repeated digits? So probability, just a reminder, is number of what we want divided by total number possible. As I so possible. So if you were doing this question, yeah.
Can you really use things that cannot be like if they're repeated, can you still use them?
Yeah, seriously. Yeah, if there's still, if it was you have repeated digits, yeah, that's actually what we're going to tell right now is what we want is no repeated digits. But is that possible that we could get repeated digits? So that's your 2 situations you're going to have to calculate. Situation 1 is what we want. Situation 2 is what's possible. So what's possible is you have 4 digits, and you can repeat digits. So you have 10 times 10 times 10 times 10, 10 to the power of 4 is what's possible. That's with repeated digits. Now you need to figure out what do we actually want. What we want is no repeated digits. So 10, then 9, then 8, then 7. Where the digit changes every time you go down the line. 10 times 9 times 8 times 7 cannot be done in my head. That's 5,040 ways. So when you see probability, you're going to have to calculate 2 things. What you want, what's possible. And then link the 2 things together. So the probability of this happening is 5,040 divided by 10 to the power of 4. And if you put that in your calculator, you should get 0.0504. I think that's correct. Yeah, it should be 0.50. There's 1 too many 10s. Definitely. See how you take these questions and you break them down. What's possible? What do we want? Link the 2 things together. So for example, 4, it says some friends are going to get a pizza. They have 10 different toppings to choose from and must choose 4. What is the probability their pizza will include bacon and pineapple? Alright. Probability. I need to do possible and want. Possible. I've got 10 toppings. I need 4 of them. Does the order in which I select those toppings make a difference? Definitely not. So it's a combination, because order doesn't matter. So I got 10 toppings. I choose 4 toppings for the pizza. And that'll tell me how many things are possible. 200. That's how many possible combinations for pizza there is. What I want bacon and pineapple for sure. So there's two ways you could do this. You could be like, all right, there's one choice for bacon, I had to choose bacon. There's one choice for pineapple, I had to choose pineapple. And then there's 8 other choices, and I need to choose 2. You could multiply all those things together. Or you could logically think it through and say to yourself, there's only one way I'm picking bacon. There's only one way I'm picking pineapple. So these two things are irrelevant, which they really are. What's one? Choose one. One way. What's another one? Choose one. Another one. And you're multiplying. So when you're multiplying by ones, it really makes no difference. So feel free to just understand situations sometimes. To be like, well, there's only one way I get a pizza with bacon and pineapple, and that's if I pick bacon and I pick pineapple. But now, how can I pick the other 2 toppings? So 8 choose 2 would tell you the number of ways you can get what you want. What does it take there?
28.
So there's 28 ways I could pick 2 other toppings and include bacon and pineapple. So the probability of getting bacon and pineapple would be 28 divided by 280. If you put that in your calculator, it's going to be somewhere around 0.13. What is it? 1. All the way repeating. Oh, that was 4.
Why wouldn't it be 4 in front of 6? There's 4 toppings and choose 4?
Because that's not, like, you're choosing 4 toppings, but that's not the pool of toppings you're choosing from.
Okay.
So remember, n always represents the first number, the number of things you're selecting from.
Okay.
So there's 10 toppings, that's what I'm choosing from. And then 4 is how many I took out of that 10 toppings.
So why doesn't like the possible just work for the entire time?
What is it?
What can't just go to 10?
If you went for 1, it was 10 and 2, that's saying you could pick bacon again. And you could pick pineapple again, which you can't. I guess technically could you get extra bacon? But yeah, like you can't pick bacon twice. And if you're saying it's still part of the possibilities, that's going to increase things, and that's not what you want to do. That's a good question. All right, example 5. It's called a birthday problem. It's actually a famous problem. You've never heard of it. So the famous problem is that if you have 30 people in a room, there's a certain probability that 2 people in the room will actually share the same birthday. And it seems like it would be extremely unlikely, right? Like it seems like a rare thing if 2 people share the same birthday. And if you calculate this, it's actually not rare at all. It's quite common that once you get to 30 people or more, it's easy to find 2 people who have the same birthday. Those 2 have the same birthday. Kind of weird that it actually happened in our class. Yeah, Hannah and Nikita have the same birthday. It's weird.
What the heck?
Yeah, so I bet you go into a room of 30. It'd be a good way to make some money. Every time you're in a room of 30, you're like, I bet someone's got the same birthday in this room. Make some money off it. Because the probability is going to end up in your favor. It's weird, but it's true. And we're going to prove it. So in a room of 30 people, what is the probability that at least 2 people will have the same birthday? At least. Well, that includes a lot of different situations. I mean, that means we could calculate 2 people have the same birthday, or 3 people have the same birthday, or 4 people have the same birthday, or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12 or 13, all the way up to 30 different times people could have the same birthday. That's crazy. So when we see things like at least, what do we want to do to calculate it? We want to use a special word. It's called the... Someone tells you got nice hair, they gave you a... Yeah, compliment. You want to use the complement. So the complement of at least 30 people have the same birthday would be that nobody has the same birthday. Correct? So the opposite of this would be nobody has the same birthday. And what we do is we take the probability of 1, that would be everything's possible, and you subtract nobody has a birthday. Alright, figure out if 30 people all have different birthdays. How are you going to do that? That's the hard part. It's kind of a crazy calculation. There's 365 days, that's for sure. So we're going to need to think about that. There's 365 days. Unless it's a leap year. Oh, that just made our odds even better. Anyway, there's 365 days. How many days do you want chosen out of that? You want 30 different days chosen. So if I'm like, you choose a day, you choose a day, you choose a day, and it's your birthday that you're choosing, then of the 365, I want 30 different days selected. So that would be like, all right, McGregor's day is October 1st. You're October 2nd. You're October 3rd. You're October 4th. Another way to think of this, so you could do it like that, and a way I think that most people would think of this in a test situation would be, we got 30 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we'll do it again. And you would say the first person, how many days do they have to choose from for their birthday? 365. How many days does the next person get to choose? 364. And you could do that all the way down until you ran out of people. Okay, that's how many days could be your birthday because all the other days before you have been chosen. No, because we're choosing, they don't share the same birthday, right? We're trying to figure out the opposite. We're doing the complement right now. So we're trying to figure out how many people don't have the same birthday. And it's going to be a big number, right? Like 364, then 363, then 2, then 1, then 0, then 59, 58, 57, 256, 255. And you could do that too, right? So 355 and then 346, all the way to 345, all the way to 336. And you could punch all that in your calculator to figure it out. That's one way to do it. If you're like, I understand the placement, the fundamental counting principle. And the other way to do it is perms and coms. Now I just put in 365 choose 30. Did I use the right thing? Does order matter in this case, or does order not matter in this case? They're picking different. Go ahead, Emma. You're on the right track. Think of it like this. So I've got Mac and Bronwyn. Mac says my birthday is January 1st. Bronwyn said Frizz. Bronwyn says her birthday is January 2nd. If I rotate those birthdays, did that change the combination of things? If you are now January 2nd and you're now January 1st, is that a new set of ways I organize the birthdays? It is. So in that case, order mattered. So should I use the C? Should have been a P. By saying P, it means, okay, it's different if Hannah's birthday is today and Caitlin's is tomorrow than if Caitlin's is today and Hannah's is tomorrow. That's different. That's a different set combination. That matters to us. So you can do that crazy calculation, or you can just go 365p30, and that's what I'm going to do. So 365p30. And that's going to give me a massive number, which I'm going to leave in your calculator. So it's going to be like 2 times 10 to the power of 760, or 76. That's huge. That's no one has the same birthday. Then you need to subtract what happens from all the possible things? So how many birthdays is possible? So before we were saying it was 365 and then you only had 364 choices left. And then you only had 363 choices left. But now we don't care. So it could be 365, 365, 365, 365, and you would do that 30 times. So 365 to the power of 30. This is what we want. That's the probability of everyone's different. Okay? What we want, everyone's different, divided by what's actually possible. And if we do that in our calculator, so 365 to 30 divided by 365 to the power of 30, you end up with 0.29. That's the probability that no one in this room has the same birthday once there's 30 of us. So if you want to figure out the probability that at least one person, you want to go 1 minus 0.29. You get 0.71 is the probability that at least 2 people would share a birthday in a room of 30. So anytime you're in a room of 30, there's a 70% chance, 71% chance, that at least 2 people have the same date of birth, which is kind of crazy because you wouldn't think that, would you? You think that's a rare situation, and it's actually not rare at all. You have a question? Huh? This is me subtracting. So 1 represents 100% chance, and then you subtract the probability of the opposite thing.
And then I would choose the 365 to the power of 30 is.
That's everything possible. So there's 30 kids, so there's 365 30 times in a row. I was saying, I don't care what your birthday is. It could be any of the 365 days. So I had to use the fundamental counting principle to figure that out. The reason I do this question is it actually is like, in the statistics world, I guess, a famous stats question because it's so like shocking. I think that out of a room of 30, which is what your average class is, that 2 people would have the same birthday. Kind of weird. Yeah. Okay. You won't get a question that's that big in numbers and that confusing, just for the record. Because those numbers are like, you're talking in like the gajillions, like they're huge numbers. So you'll never get numbers that big. But it's fun to just check it out. You have the rest of today to work on your unit assignment.